Okay, let's get started, everyone. So today we are going to pick up from where we left off with BERT, and we are going to talk about both the pre-training and fine-tuning phase in a little more detail, and then we will expand our discussion of fine-tuning to decoder and prefix LM-based configurations of transformers, and conclude with a discussion on instruction tuning. So just a roadmap for next week. On Monday, we will discuss some of the elements of transformers that we haven't covered in too much detail, such as the position embeddings and the tokenization, so how you split the input sequence into words or tokens. We'll cover some of the common algorithms for doing that. And then on Wednesday, we will proceed with a discussion on what's called as preference tuning, or classes of algorithms that learn from human or AI feedback, such as RLHF. Okay, so I do want to mention that this structuring of the course is a little different than last year. Last year, we spent a lot more time going through how you can use BERT for various tasks. This year, I'm going to skip doing that and instead focus more on decoder-only models and how we can align them. All right, so let's get started with our discussion on BERT, which is what we ended the previous class introducing and briefly discussing. So again, BERT is an example of an encoder-only transformer. And when it came out, it was pre-trained on the largest data set anyone had pre-trained a language model or a transformer It was the largest model to that point, and it set the state of the art on a wide variety of tasks, which suggested the power of this pre-train on large data and fine-tune on smaller scale data paradigm that has continued into today. So again, there were two stages. So in pre-training, training objective is self-supervised, and we discussed the masked language modeling objective for pre-training. So why is this a self-supervised objective? Can someone tell me? Yeah, so remember how we introduced this masked language modeling objective, right? We take any piece of text, we randomly select some percentage of the tokens to replace with a masked token, and then we run through this transformer network and predict the identity of the masked words. So as long as I have any piece of text, I can just do this without any sort of additional human labeling or data collection, right? Hence, it's a self-supervised algorithm. As long as I can collect text, I can generate data for masked language modeling just like I could for left to right next word prediction. So it's the same class of objective as the normal language modeling objective. Okay, so that was pre-training. And then we discussed briefly how when we pre-train a model, our goal is not to solve any one particular task, but rather try and encourage the model to learn as much as it can about the language, its properties, and things like world knowledge in addition to syntactic structure. So these are all properties that could be useful in solving any particular downstream task, but the model is not specialized to solve any one task like sentiment analysis or a question answering. It's kind of like a general purpose backbone that can be adapted to solve various tasks. And that adaptation process is called fine-tuning. So in fine-tuning, we're talking about a process of adapting a pre-trained model to a particular downstream task. So remember, last time we also discussed this word downstream task that refers to any specific task that you care about solving as part of your job or whatever. Like it is not a general purpose task, right? It's a very specific task that you care to solve. And the way you're going to solve it is by taking a general pre-trained model and then adapting it via whatever method you wish. And so last time we had discussed fine-tuning as one of these algorithms. Okay, so let us talk a little bit more about both of these steps in the context of BERT. And then we will expand our discussion of fine-tuning to decoder-only language models as well. Because there are some details about BERT that I left out last class, so we will also go through that here. So in the pre-training phase, just as a review, we had this sentence, students, and then we replaced the next word with a mask token, their books, right? And so given this input, we get a word embedding for every token. So even the mask, this mask token is a separate entry in our vocabulary. So, along with words like students, open their books, we have a special mask token that has its own embedding. And whenever we replace a word with a mask token, we use the mask embedding instead of that word's embedding, right? So this embedding right here, this is not using the embedding for opened, but rather the embedding for mask, just to be clear. All right. So now we pass all of this into unmasked multi-head self-attention, right? And so this can be unmasked because we no longer have to worry about seeing the word that we are trying to predict because it's just removed completely from the input. So the model has no idea what this word is. So then we get a couple of vectors as output. And unlike in a decoder-only model, where we put the softmax layer on top of every single final layer representation, with BERT, we are only trying to predict the next, a word at the position of a mask token. So here, we're trying to predict not the next word, but the missing word, right? And so this is why we have this name of masked language modeling. So instead of predicting the probability of a word given all of the previous words, here we're trying to predict the probability of word sub I, which is the mask token, given all of the unmasked words before I and all of the unmasked words after I, right? And so even if we have 30% of the tokens that are masked, when we're predicting this particular mask, if there's another mask token in the sequence, that's also part of this conditioning to predict the word at this position, right? It gives us no information about the current masked word. So basically, the full sequence is fair game to attend over. There is no chance that you can cheat in this task. Is that clear? Are there any questions about this pre-training task? Okay, let me check on YouTube. All right. Okay, so there's one thing that I have not mentioned so far, which is that in the BERT model itself, the authors introduce a special token at the beginning of every sequence. And they call this the CLS, or classifier token. Actually, let me draw this in a different color just so it's clear. Maybe I'll use the same one as mask token, just to emphasize that this is a special word. So CLS is a special token. It's added to the vocabulary just like mask. It has its own embedding. And the CLS token occurs at the beginning of every input sequence. Okay, so why do we have this thing? The reason is because when BERT was being created, people were very interested in solving classification tasks. So is this sentence positive or negative? Or does this sentence entail this other sentence? Even problems like question answering were converted into classification-based frameworks. Is this phrase part of the answer to the question or not in a passage? And the authors wanted an easy way to access a representation of the input such that they could put a classifier over it to predict whatever it is that they actually wanted to do. For the sake of pre-training, they actually have a special objective function over the CLS token. Oops. So this one also goes through the unmasked self-attention. We have many blocks of this. This whole model is called BERT. But then this token, the CLS token, is never masked. It's always preserved as part of the sequence. And the authors decided that maybe they should have a special training objective for just this one token such that the model knows it should be used for classification tasks. So if you read the original BERT paper, there's a special objective here called next sentence or next sequence prediction. And the way they pre-trained BERT is they took two different input sequences, they stuck them together, and some of the time the second sequence directly followed the first sequence in the training data. Other times it was just a completely random sequence that did not follow the first sequence. And so they formed this binary classification task. Does the first sequence precede the second sequence in a document or not? And they put that over the first token. They trained it with a classifier, and they found that they could now use this first token representation to as input to any sort of classifier. I'm not going to go into any detail on this because subsequent papers found that you could just remove this objective with no effect on the performance on downstream tasks. But I will mention it just because if you read the paper, you will see this and you might think it's a critical component of the model. In reality, you don't need this at all, and you can just leave the CLS token as part of your input during pre-training, and it will still be just as useful during the next step. So that is the pre-training phase. Now let's get to the fine-tuning phase. So in fine-tuning, we are now trying to adapt our pre-trained model to some specific task. So let's say we are going to look at sentiment analysis as an example. So in sentiment, I have an input, and it's either positive or negative. So I have a binary classification task. So how do I use this pre-trained model for binary text classification? Let's just take a simple example. So I have my CLS token, of course, and I have this sentence, the movie was good. So note, at fine-tuning time, we are no longer doing masked language modeling, right? Masked language modeling was just a vehicle by which we enabled the model to learn all of these linguistic properties about the training data that we gave it. But now we are interested in sentiment analysis. It doesn't make sense to add mask tokens to an input. What if we mask the word good, right? Then there's no way the model can predict the sentiment of the sentence. However, we want all of these tokens to pass through BERT. So this is the pre-trained model. Maybe I'll make this more clear. Let's see if I can use a different color here. So we will call this the BERT model. And I'm showing it in a different color to indicate that this module was pre-trained already on the masked language modeling task that we discussed earlier. So now we're going to feed a new sentence into BERT, this time unmasked. And what do we get as output? We know that we will get a vector for each token in the input. So now I have 5 vectors, right? And I want to make one decision over whether this entire sequence is positive or negative. So this is where this CLS token comes into play. The designers of this model wanted an easy way to access the content of the text, and they decided that the model should use the CLS vector in order to do this. So basically what they do is put a softmax layer here to predict positive given just this vector of the CLS token. So if you look at this, you might be wondering, we're just putting this classifier over the very first token representation in the sequence. Does the model even have information about the full sentence in this vector? So does this vector over here encode information about this full sentence? Any ideas?
It is, because the attention will be calculated based on the query of the CLS with the key other tokens. Or we have the weighted value to represent the full information of this.
Yeah, exactly. That's correct. So remember, the critical thing with BERT is that it is an unmasked self-attention, right? So the query key dot product of this first token is not masked to include just the current position. It has access to the full sequence, even the future tokens, which is why this representation has access to all of the words in the sentence. Similarly, so does this one, and this one, and this one, and this one. All of them are fully contextualized with all of the other words in the sentence. So just by design, we decide to use this CLS vector, which occurs at the first token in the sequence for convenience. But you could also imagine other ways, right? I could take all of these vectors and average them together and then put them into a classifier. I could do something else, maybe use another composition function, put a recurrent neural network on it if I wanted to. But the key finding of the BERT paper is that this kind of classifier can be as simple as possible as long as the pre-trained model is very, very large and trained on a lot of data. You don't actually need to add more task-specific parameters beyond the bare minimum, which in this case is just a single classifier. So let us actually look at what it means to predict positive, just to be clear, make sure everyone understands the concepts that we've been discussing this semester. So when I say predict positive, I'm using the exact same softmax layer that I was using in language modeling to predict the next word, or in masked language modeling to predict the identity of the current word. However, in this case, I only have 2 labels, right? I have positive and negative. In the language modeling case, I have V possible labels, where V is the size of the vocabulary. So this is a much smaller softmax layer than what we are used to from the previous models. So just to be clear, let's call this representation H of CLS. So we are interested in coming up with a distribution over like positive and negative. right? So this is similar to our distribution over the entire vocabulary, but here we only care about positive and negative. So let's call this O, as we did before. Now, O is just equal to the softmax of, let's call this WOHCLS. So what is the dimensionality of W sub O? You can see that it should be 2 by the dimensionality of this hidden state, right? As opposed to a V by D, which is what our language modeling softmax matrix would look like. Other than that, it's the same exact computation that's happening. So you can see that by training the model on this kind of objective, we are specializing it to do this sentiment analysis task. The resulting model may be worse than the pre-trained BERT model at predicting the masked word. And that's fine, right? Because no one actually cares about the task of like predicting a single masked word. We care about the downstream task, in this case, sentiment analysis. And this is how we maximize our performance. So let's also discuss a requirement of fine-tuning. So how do I actually do this process? I need some data of the form input sentence, sentiment label, right? So this is not a self-supervised process, fine-tuning. So fine-tuning is not self-supervised. It generally requires a human-labeled training. Wow, what? Sorry. Training data set for the downstream task. So I omitted human here because these days you can also use language models to label a training data set for you and then perform this fine-tuning process. But yeah, generally this is not a self-supervised process because, you know, in this case you need inputs from a specific domain or source, right? You need sentences that contain some sentiment, either positive or negative, so I can't just pull any arbitrary sentence. And once I get sentences that contain sentiment, maybe I crawl like IMDb reviews or something, I still need to get the label, positive or negative. So this makes this, this process generally uses far less data than pre-training. In pre-training, I can basically get infinite data. In fine-tuning, I have a small, finite amount of data that I can use. All right, is this clear, this process? Yes?
When you do fine-tuning, how much does it affect the language model? What happens if the fine-tuning goes after this fine-tuning?
Yeah, so the question is, if we do fine-tuning, let's say on sentiment, how does that affect the performance of the language model itself on its pre-training objective, like masked language model? It's a good question. So let us look at, say, the gradient flow through this fine-tuning process, right? We start with the pre-trained BERT, which has been optimized on one task, masked language modeling. And we have our softmax layer here. The model predicts positive. It gets some cross-entropy error, which we backpropagate through the CLS vector into the pre-trained BERT model and into all of the token level embeddings for the sequence. So what is getting updated here in the fine-tuning process? The embeddings are definitely getting updated. What else is getting updated? The weights, right? So at every block of BERT, I have WQ, WV, WK. I have that big feed-forward layer that we use after the concatenation of all of the head vectors, right? I have a huge number of parameters in this model. All of them are part of the gradient computation with fine-tuning, and all of the parameters are getting updated. So to your point, we have a model that was once optimized for masked language modeling, but all the parameters changed to kind of lower the loss on the sentiment task. So the resulting model is not going to be as good on the original task of masked language modeling. And in some cases, you can even do like multi-stage fine-tuning. So I could fine-tune my BERT on sentiment, then I could fine-tune it on question answering, then I could fine-tune it on another task, and people have seen some gains in doing this as well, but always what you care about is the performance on the last task. The performance on all previous tasks will degrade as the model like forgets some of those abilities. Other questions? Yeah, so the question is, this process right now, I've shown affects all of the parameters in the pre-trained BERT model. Is it ever beneficial to not update some of the parameters and only update, say, a small fraction of parameters? The answer is yes, and we'll look more at parameter-efficient adaptation methods later in the semester. But broadly, you can imagine several reasons why you don't want to update all of the model parameters. One is just computational expense. So if, for example, I freeze the first 23 layers of BERT and only use the final 24th layer for fine-tuning, I don't actually have to compute the gradient through all of those layers, right? So that becomes a very efficient strategy if you are constrained by your hardware. Another reason is that if you adjust fewer parameters, the resulting model is more adaptable because you have one part that can be shared across many different models, many different downstream tasks, and maybe you only need to provide a small subset of parameter adjustments in order to specialize the model. So we see methods like prompt tuning that add like 0.0001 new parameters to the model, which really give you many of the same gains as full model fine-tuning without the storage expense of creating a whole new model. All right, let's see on YouTube. Okay, great. So now let's extend what we just talked about to autoregressive language models or decoder-only language models, because this is now getting closer to what we see in today's language models. So fine-tuning a decoder-only language model. So let's say we wanted to solve the task of sentiment analysis again, but this time we have trained a next word prediction language model, right, with masked self-attention. So in particular, I might have a model like, I might have the same input, the movie was good. And now I have a couple different options on how I want to proceed with training this model using a decoder-only model, but fine-tuning it for this task. The first one we're going to look at is quite simple. So I can just reframe this as a text generation problem and use a prefix LM mask to accomplish the fine-tuning process. So in sentiment analysis, I always assume I have an input sentence, right, or text that I want to judge the sentiment of. So this part of the prefix is going to be unmasked. So we'll feed it to our partially masked multi-head self-attention. And I get some vectors here. And again, these can all see each other because I assume I have the full input text. Now, my goal is to predict the sentiment of this, this text, right? So I could do this with just a one token prediction. In fact, I could say at this final hidden state here, I want to generate the next word. I could train this model to predict positive. And this allows me to use this text generation model and allows me to use the same softmax layer that I did before during the pre-training of this decoder model. However, it comes at some cost of maybe this model isn't going to be as good as just putting a binary classifier on this next word. So let's see how this actually works. This distribution is going to be the size of the vocabulary from A to Z. And we know, like by definition of this task, that the only acceptable outputs are positive and negative, both of which are entries in our vocabulary. However, we have like V minus 2 other words in our vocabulary that we want the model to assign 0 probability to, right? So my ideal distribution might put, you know, like, I don't know, 30% on negative and 70% on positive. Anyway, the way that I compute this distribution is the same as before, WO H sub good. But here, the WO is of the size V by D. So we're using the same softmax matrix during pre-training. So one distinction to make is that in BERT, this W sub O here, this is a new parameter initialized randomly. So why is it a new parameter? Because during pre-training, we were never predicting positive or negative, right? We were always predicting into the whole space of the vocabulary, what is the identity of the missing word. So this parameter here never existed during pre-training. So during fine-tuning, we add this new W sub O matrix, and we randomly initialize it, but every other part of the model is initialized with the pre-trained BERT model, and then we do gradient descent on the result. In this case, it's a little different because we are actually using the same W sub O that the language model was pre-trained on, because we're treating this as a text generation problem. So this might not make sense right now. Like, why would we want to do this as opposed to put a new classifier over this this model, over this hidden state that just had 2 classes, because we know we only care about 2 classes. However, it becomes a little more apparent when we go to more complex tasks, right? What if I had a task where the output was not just a single label like positive or negative, but it was rather an entire sentence? Maybe instead of just predicting the sentence or the sentiment of the sentence, you had to also explain why you predicted positive or negative, right? In this case, this task cannot be formalized into just a single classifier. You might actually need text to be generated to solve your task. So this kind of thing, fine-tuning pre-trained decoder model. And examples of this are like GPT-2 that you might actually use in this class in the project, or GPT-2 or Llama 2 or other models like this. These are all just giant pre-trained decoder models, right? But you can still fine-tune them, but it's useful for text generation tasks. That's not to say that you can't do the same thing that we did for BERT and just learn a new classifier at the final hidden state for whatever task you want. It's just that this is primarily the way that we use decoder-only models because they are the only ones capable of generating text, and we can share that same softmax matrix. However, we will see when we start talking about RLHF that this framework is also used to learn reward models, where instead of having this softmax here over the whole vocabulary, we instead formulate this as a regression problem, where the model is trying to predict a number that indicates its preference of a particular preference. But we will get to that later, so you don't have to understand what I just said right now. All right, so how do we fine-tune for text generation? In text generation, we might have an output sequence of tokens rather than a single word. And so this process proceeds basically the same as before, and now we will see how our prefix LM mask works. So we might have this movie was good be part of the input, and something like positive because of good, or some explanation, right? That I wanted to just generate multiple tokens. So when we look at the fine-tuning mask here, we have, again, that prefix LM mask, right? Where the input part is completely unmasked, and then the output is masked, and this is set to -infinity. Does this make sense? So this is how we might fine-tune a decoder-only model for some downstream task that we care about. In this case, this weird like sentiment, but also explain why you picked the sentiment task. All right, any questions? Yes?
I was wondering, so in the state of art today, what do we use for classification?
So the question is, for the state of the art in today's, like for text classification, what is the best model? Sadly, it is probably just prompting GPT-4, which requires no fine-tuning. However, as we'll see actually later in this class, GPT-4 itself is the output of multiple stages of instruction, fine-tuning, and RLHF. They may not be on your specific task, but we'll see that this kind of method allows the model to generalize to arbitrary like text classification tasks, including one you might want. So yeah, the state of the art today is take your task, put a couple examples into the prompt of GPT, write an instruction about what you want it to do, and it will likely perform better on some arbitrary task than any other model. However, if you have a lot of training data for your specific task, you will still get better performance by fine-tuning a smaller model, actually adapting its parameters to that task. But GPT-4 works well when you have like very few training examples, or the task is very complicated. So even if you had a lot of training examples, a smaller model might not be able to learn how to solve the task.
I guess it's now it's a question of the resources that you can use to effectively get the same amount of accuracy.
Yeah, so if you have a compute budget, then yeah, you can only do so many things. But there are a lot of very efficient tuning methods out there that we'll talk about later in the semester. All right, other questions? Yes?
Considering our training example to be more diplomatic, like the movie was not bad. So how does it deal with that type of situation? So we have an emoji embedded which misconveys or injects the prompt in a different way that how it is going to be.
Yeah, so I guess your question is, what do you do when the text is kind of ambiguous and not obviously positive or negative? Yeah, so the way I frame this is like pretty binary. It's either positive or negative, but in actuality, most sentiment analysis data sets are more fine-grained than that. So they might have a neutral category. They might have a different valence for sentiment. So you could have like strongly positive, mildly positive, neutral, and so on. But I think, yeah, in cases like the movie was not bad, right? That could be perceived as kind of negative or positive depending on how you view it. But yeah, in terms of the model, like its behavior is determined by the training data that you give it. So depending on the labels that a human gave to those kinds of examples, the model's behavior would change accordingly. Yes? The question is it important to balance the label distribution when you're, say, fine-tuning a language model on some data? In general, that is good practice, especially if you have a very skewed distribution. However, yeah, I mean, I think it just depends on how much data you have. Most strategies for dealing with this imbalance are, like downsampling the dominant class while you're doing fine-tuning. I think as you get larger and larger base models, it likely matters less. They should still be able to pick up on the patterns between the different classes, but definitely for smaller models, if you have a data set where like 90% of the examples have one label, they might just learn the majority class baseline. Yes? Mm-hmm. So the question is, here, when we were talking about fine-tuning BERT, we introduced this completely new parameter, W sub O, which allowed us to get this probability distribution over two classes. So this WO is not sharing any parameters with the softmax of the pre-trained model. Oh, this one? Oh. Yeah. So, okay, that's a good question. So here, our softmax is over the full vocabulary. Let's think about what the training distribution looks like. So remember, when we're computing the cross-entropy loss, we have a ground truth target distribution that we're trying to match. So in our, let's say, training distribution, we will either have 100% on negative and 0 everywhere else, or we'll have 100% on positive and 0 everywhere else. So if you fine-tune your model with, say, 20,000 examples where the target is either 100% negative or 100% positive, the model is never like reinforced to put any probability on any other token. And so just by gradient descent, it will learn that these are the only two possible options. And you can actually see that behavior emerge when you look at the fine-tuning dynamics. Like after some point, there will just be very, very little probability elsewhere.
The other question was that how do language models deal with something like psychiatry, because those are like maybe understanding by humans, but for the language model it may not be that good.
So the question is about how can a language model understand sarcasm. This was actually one of the motivations behind this pre-train and fine-tune paradigm, because if you just did fine-tuning from a random model and you did not do any sort of pre-training, then your model has basically no chance of learning things like sarcasm through its training process. You're limited by a very small amount of labeled data. Pre-training, however, you can scale to as much data as you want. So you might have many different examples of sarcastic phrases. You might even have people who have been on the internet and explained the meaning of various sarcastic expressions, or people on forums saying, oh, I meant this sarcastically or something. So the model during pre-training has the ability, when it's predicting the next word, to learn all of the associations between these different texts in its pre-training data, and then apply that knowledge during the fine-tuning process. All right, let me check the YouTube. All right, pretty dry here. Did someone else have a question?
Aren't we using the same W matrix for like all the next predictions?
Yes.
So when we fine-tune it, do we introduce like a new one for the positive negative?
So in this case, the question is, when we fine-tune in this text generation setting, do we introduce a new W sub O matrix at fine-tuning time that's different than the one at pre-training time? The answer is no. We initialize this matrix with the pre-trained one, and we update it via gradient descent. So there's no new parameters here. Maybe I'll make that clear. no new parameters. But in this case, we added this new W sub O matrix.
Just to follow up on that, like, are we making sure that the answer of the LLM, like the first word would be positive or negative? Or?
Yes, you're doing that by teaching it through your training data that the first word after the input is always positive or always negative.
So this won't be self-supervised?
No, this is not self-supervised. And I hope you can see through like this kind of example that this process can be generalized to arbitrary text generation tasks, right? So I can take a pre-trained decoder and fine-tune it on whatever sort of sequence level input and output task I have. So it could be like summarization, for example. My input could be a long book. My output could be a short summary of that book. That's still a sequence of tokens. We can use this exact setup where the input is fully unmasked and we do the masked loss for the target tokens. Okay, so now let's kind of generalize this fine-tuning process on decoder models that we've been talking about. So currently, I just made up this random task of predict the sentiment of a sentence and then explain why you did that. But that's a very specific task. I mean, maybe no one would really care about it. In general, we want a model that is good at following our instructions, right? So let's say that we pre-trained our model. It turns out that a pre-trained next word predictor is not really good at following the instructions that you give it on many complicated tasks, right? So if you've ever used ChatGPT for something very complicated, you'll know that it actually does a pretty decent job in many cases of following even like complicated paragraph-long instructions that add numerous constraints into what the model's output can be. Oftentimes, you can't really expect this behavior to emerge during pre-training itself because, I mean, we see lots of interesting examples where if I say something like, write me a happy birthday message, that's an instruction that you might expect the model to actually follow your instruction, but instead it might just generate similar instructions like write me a wedding message or write me and it's not following your intent. Similarly, you also have cases that have very complex and novel instructions, and you might want the model to generalize. So basically, like, there's a motivation where we want the behavior of the language model to align more with its use as a tool to help us solve things rather than just generate arbitrary text. And so this is where the motivation for what's called as instruction tuning comes in. And so this is basically using fine-tuning. And actually, nowadays in papers and material you might read on large language models, we see fine-tuning referred to as supervised fine-tuning, which is kind of redundant, or even SFT, which is a quite popular acronym. So if you ever see SFT in any like blog post or tweet or paper, it is referring to just this process above of taking some labeled data and fine-tuning your pre-trained language model on it as a text generation model. All right, so our goal is make the pre-trained model more capable of following instructions. And so we are just going to look at the first part of this process, which is doing SFT on instruction following data. However, the real successes here are due to preference tuning methods such as RLHF, which we will talk about later. But instruction tuning is very easy to understand conceptually, so I wanted to just discuss it right now as probably the most important class of fine-tuning methods. So just another high level, the method is just standard fine-tuning on a special data set. So we're not going to introduce any new method other than this up here, but the data set that we're collecting for instruction tuning is very different than what it would look like for like sentiment analysis or any specific task. All right, so let's get to the actual method here, which, as I've described, is just a data set of instruction on what tasks to solve and corresponding outputs of that task for a couple of examples. So this, the goal here is not to solve one particular task, but instead to teach a model how to follow instructions to solve arbitrary tasks. And so here, sentiment analysis could just be one example of an instruction. I might have an input like, please assess the sentiment of the sentence from 1 to 5, and then give it the input, and then have a corresponding output that the model needs to generate. In the same data set, I might have, please answer the following question about this paragraph, and have an output be the answer. Or I might have, please write a short summary of this story, and have a corresponding output, right? So all of these inputs and outputs for different tasks are getting glommed together into one data set where the input is always the instruction for a task and the output is an example solving that task. But we are not focusing on one specific task here. We are focusing on just general ability to follow instructions. Does that make sense? So let's look at one particular example here. Please answer the following question and provide a detailed justification. So this is generally considered the instruction part of the prompt. In sentiment classification, we would not have this instruction, right? We would just have the input sentence, and the model is being fine-tuned only for sentiment. So it knows through the data that it needs to produce either positive or negative. In this case, we have many different tasks, so we actually have to describe the nature of the task to the model. Now we have a specific input, right? Input, what was the average of the 685 spring 23 midterm? I don't know why this is the, and so now you might have the corresponding output, which is what the model needs to generate. It might say, I can't answer that because the piazza is private, or something like that. So you can see here that the output could also be a sequence of tokens, which is why we are using this pre-trained decoder-only model. And the way this works, again, is we have some pre-trained LM. It takes as input the instruction and input pair, and it produces the output. And remember, this is the fine-tuning process, right? So we're going to apply backpropagation and gradient descent to update the parameters of our pre-trained model on this particular task. So just some highlights of this approach. First, instruction tuning focuses on many different tasks at once, not just one. And instruction tuning improves generalization on tasks outside of the training data. Oops, let me say the fine-tuning data. So this second point is very interesting. Basically, it's saying that if you gather a large and diverse enough set of instruction input-output pairs and you perform instruction tuning, the resulting model is then better able to solve new tasks that were not even in the instruction tuning data that it saw during the fine-tuning stage. And so this is a really interesting finding that first appeared in this Flan paper by Google researchers. So I'll briefly just switch to the display to show you some examples of what that looks like. Sorry, you have to add the display again, which is annoying. Okay, so let me just go to the course website. We can check out some of the tasks that were included in this paper. So just looking at this first figure is quite interesting. So we see here two different tasks. One of them is common sense reasoning. So here's a goal: get a cool sleep on summer days. How would you accomplish this goal? Options. Now there's two options, and the model is fine-tuned to generate one of the options. In the exact same data set, we have a translation task. Translate this sentence to Spanish. The new office building was built in less than 3 months, and we have a target. So the model is trained to solve both of these tasks in the same data set, right? And the nice thing is that if we, at test time now, give it an instruction for a completely unknown task, like this one, does this premise sentence entail this hypothesis sentence, and you give it these options, it turns out that the model is actually able to better solve this kind of task than it would be without instruction tuning. So if we look at this plot, we can see some evidence. This is using GPT-3 with zero-shot prompting, which means that for this input, I just feed it as a prompt into GPT-3, the language model trained on next word prediction, without any sort of instruction tuning, and it gets 42.9%. And we see that this FLAN model, which is being tested on unseen tasks, is outperforming these state-of-the-art models at that time with just this instruction tuning method applied to the base model parameters. So this is a very powerful technique that a lot of companies are now investing considerable money and resources to gather more and more complex instruction tuning data sets. These data sets are also used to generate outputs that humans then score for methods such as RLHF. All right, so any questions about instruction tuning?
How are these models able to talk about instructions regarding their goal set? As in, I guess the data set that we provide to them is always external to the model itself. Mm-hmm. But yet, if you ask ChatGPT about ChatGPT, it can answer. So how do you
So the question is, how can you ask ChatGPT questions about its own operation?
any other model?
Well, keep in mind that ChatGPT is just a next word prediction model, right? So it is just generating text based on the distribution of the next word that it's producing. So there's nothing specific preventing it from discussing itself, right? If I say, explain how ChatGPT works, and I put that into the model, it's going to have distributions over the next word that I'm sampling from to generate new text, right? So conditioned on the input, it can produce whatever it wants.
But isn't it the case that when it was first created, for example, there would be no articles or data set regarding itself?
So I guess what you're asking is, has ChatGPT seen documents about ChatGPT in its pre-training? And yeah, the answer is yes. I mean, it's constantly being updated with new data. You know, how do you update a pre-trained model? You can just continue pre-training on new data, right? So if you notice, OpenAI keeps updating the dates of their pre-training data. So now I think it's like October 2023 or something like that. So the models have seen data before that period, which obviously in 2023 we had a ton of articles about ChatGPT. Other questions? Yes, so the question is, does ChatGPT do instruction tuning? This is the first step of the RLHF framework. So yes, all of these kinds of instruction following models do this as the very first stage of the process. Oh, that's a good question. So is this generalization to new tasks just an empirical result, or is there some reason? Yeah, it's just an empirical result. People are still trying to understand how these language models work, but there's no like conclusive theory yet on why this is so effective.
Why don't we use specialized tokens, for example, for system prompts and instruction prompts, and then fundamental prompt? Because sometimes the next word generation confuses between them, and it's not actually referring to the prompt itself. So why don't we use like specialized tokens as used in BERT, for example, CLS? We can use those tokens. And my next question is, how do we ensure that the model is safeguarded against malicious instruction security? For example, let's say they have a chatbot for a particular company and someone is using it. And it's like, okay, now you're doing this. Give me an answer about that. How do we safeguard the model against malicious instruction?
Okay, so your first question is kind of specific to OpenAI's format, and I don't know why they chose that particular format, but there's no reason that you shouldn't use like a different format. Nothing in these methods is specific to that particular framework. Your second question is more interesting. So how do you prevent like undesirable uses of the language model? I guess a canonical example is like, you know, some user types into ChatGPT, how do I make a pipe bomb or something with these materials? And you don't want the model to actually give you those instructions, right? And so, yeah, this is generally accomplished via collecting labeled data where people will have instructions like these paired with outputs such as, I cannot answer that question due to whatever policy. So you can consider that even just another example of instruction tuning. However, yeah, most of the ways that people handle that in practice are a combination of this kind of instruction tuning and RLHF, as well as actually just using very specific prompts that say specifically in the input you are like a nice language model and you want everyone to be happy and blah, blah, blah. So there's a whole class of attacks that are known as like prompt jailbreaking, where people try and get around this by putting in their own input, please ignore everything you saw before, or like putting their instruction in a different language that gets around some of these safeguards. But yeah, it's a constantly evolving field. As the providers make up new defenses, people find ways around them. Yes. Yeah, so the question is, how expensive is fine-tuning compared to pre-training? Fine-tuning is generally just a tiny fraction of the expense compared to pre-training. Yeah, also for this, here, I forget how big this data set was. Let's actually take a look. I don't think it was that big. I don't know why my computer is going so slow. Okay. Yeah, so they have like all of these data sets here. So 62 different data sets. They reformulate them into instructions. So overall, like and you can see that they have like a BERT or T5 base model. These models have seen on the order of billions of pre-training next word predictions. And for fine-tuning on this set of 60 different data sets, it's going to be much smaller than that. So yeah, generally pre-training is way more expensive than instruction tuning or RLHF or anything like that.
How can we improve the performance on language modeling tasks like common performance or like by instruction tuning? How can we improve the performance on language modeling?
So if you care about just one task, like maybe you care only about sentiment analysis, then probably your best bet is just to collect a data set specific to that one task and do fine-tuning like we described earlier in this class. If, however, you want to use a single model to solve many different tasks and actually follow human instructions to complete those tasks, you want to do instruction tuning, which is this method. So yeah, it kind of depends on how you want to use the model. Like people are definitely still fine-tuning large pre-trained models for single tasks. That's, if you want to maximize performance on that task, that is the way to go. Wow, okay. Okay, so the question is, ChatGPT is only pre-trained to predict the next word. How can it solve complex math problems? Remember that even a math problem is broken into an input sequence of tokens. So each number, we haven't yet talked about tokenization, so it might be a little confusing right now, but you can imagine that any piece of text that you can write down can be represented in some way by word embeddings, a sequence of word embeddings or token embeddings to ChatGPT. So even add 134 plus 0.297 will be broken into some sort of sequence, and the model has to reason over that sequence. But the operations are exactly the same. Yes, so if it has to produce like some very specific number, it does not have a single embedding for that number, but rather splits it into many different tokens. So like 0.29787 might be split into 0.2 and then 5 and then 7, 9, 7 as all separate words. Well, this will be more clear on Monday. All right, other questions? So the question is a relationship between few-shot prompting and other like prompt engineering methods compared to instruction tuning. So in prompting, we are doing no updates to the model's parameters. Prompting basically refers to modifying the input sequence to my language model, but I'm not updating the model in any way. Instruction tuning is just an application of fine-tuning. So the model, we are computing a gradient and updating the model's parameters to lower the loss on whatever our objective is. So yeah, the two are completely different methods. Any other questions? All right, so let's end a little early today, and next time we will talk about the point you brought up, how do we get an input sequence for arbitrary text? And we will also talk about position embeddings, which is the one component of the transformer that I have not discussed in detail yet. So see you on Monday. Oh, oops, I forgot all about the YouTube questions. Hang on one sec, let me just answer these. What is the upper limit for the size of instruction tuning dataset and compared to the pre-training dataset size? There's no upper limit, it just depends on how many instruction input-output pairs you can collect, which is generally far smaller than the pre-training dataset. When fine-tuning BERT, how are the CLS tokens utilized? They are used for classification. Basically, the vector at that position is the input to a classifier. And they encode the information about the full sequence. What is the intuition behind why or how it's working on never-before-seen instructions? That is a great question. I don't have a good answer to it. Yeah, I mean, maybe in the linked paper they might have some intuition, but there's certainly no theory behind how this is working. How can we instruction fine-tune the foundation model to learn to reason? Or is it generally not possible given all it's doing is predicting the next word? Well, predicting the next word requires a lot of reasoning as well, especially with very complicated contexts. Like going to the example before, if I ask the model to solve a complex math problem, just because it's predicting the next word, if it's going to do it correctly, it needs to actually do all the reasoning somehow in its parameters and its attention in order to predict the correct answer, right? So predicting the next word is an easy way to say, like, these models are not doing anything intelligent, they're just predicting the next word. But if you think about it, that's actually a very complex task given a set of very complex instructions. So yeah, the model will have to learn to reason to solve such tasks. All right, sorry about that. I will be more attentive to YouTube in the future and see you all on Monday.